Ginberg Landau theory, okay, that Alokster will discuss in statistical physics in detail with derivation. Okay, I want to discuss one more topic, like what will happen when you apply AC fields to superconductor. Okay, that is not mentioned in the syllabus, but I like to talk, and there are some small more topics are remaining, but those topics I will cover when I will finish this free electron theory. Okay, that will you will have much, you can appreciate more about those properties of superconductor. Okay, so today I'm starting with lattice dynamics. Okay, lattice vibrations. New topic for the adding lattice vibration. So lattice vibration. Okay, there's still 1 minute remaining. I think students still are joining. Okay, let them join. Then we can start. So lattice vibration, as all of you know, what is lattice vibration? Okay, so your lattice vibration is basically nothing. Okay, it is.
Hello,
So this is an oscillations of atoms. Okay. Hello. Anyone?
Sir, hello, sir.
बोलिए.
I have one doubt from previous lecture. Can I ask now or?
No, you can ask, you can call me on WhatsApp. Okay.
Okay.
And for doubt class, I will arrange one more class extra. Okay. So today I have made a test also for superconductivity. Okay. That test will be given to you up today, and maybe possibly today night or tomorrow morning. Okay. And then after that, I will including the test doubt as well as your personal doubts. I will give you some more time. Okay. So let me continue with
Okay.
this lattice vibration. So lattice vibration is basically your oscillations of atom. Okay. So here, what do you mean by lattice? Okay. So lattice, okay, you have a points arranged in space. Okay. So here I'm talking about the crystalline solid. Okay. So we have atoms placed on these points. Okay. So this form a regular lattice. Okay. And these atoms in the solid, in crystalline solid, can be considered as a harmonic oscillators. Okay. So these atoms are not independent. Okay. So when I give the amplitude to this atom, okay, they vibrate collectively. Okay. So we can assume a solid is made of harmonic oscillators, okay, or harmonic atoms. These atoms form as a harmonic oscillators. Okay. These are springs. Okay. So this is my, okay, this is my lattice, or these are all springs. Okay. Or spring constant, say beta. I'm using, generally we use k word, I'm using beta word here because k we'll use for wave vector. Okay. So this is my model of lattice. Okay. Now the word is lattice vibration. Okay. So why we should study lattice vibration first of all? Okay. So lattice vibration, okay, is the study of lattice vibration is important. Okay, because it will tell you how solids absorbs heat or energy. Okay. So lattice vibration study, why it is necessary? So lattice vibration, okay, why it's important study? Okay, because it will tell, okay, it will explain how solid will absorb heat or energy. Okay. So in solid we have two things. One is at atom and other is electrons. So जब भी you give supply energy to your sample or your solid, okay, that heat or that energy, either it will be absorbed by your atomic vibrations, okay, by atoms, or it will be absorbed by your electrons, okay. So when you supply heat to a system or system absorb energy, solid absorbs energy, okay, these atom will vibrate. Now because these atoms are not independent, they are not isolated. So suppose this one atom is vibrating, so with this atom, this nearby atom will also vibrate, okay. So this combined oscillation, okay, due to heat or energy, that is called your lattice vibration, okay. Okay, and the study of lattice vibration is key, okay. So lattice vibration is key concept in solid state physics, okay, key concept in solid state physics, okay, to explain temperature dependent properties of solid, temperature dependent properties of solid, okay, the properties which generally depends on temperature, okay. So there this is the key concept, okay. For example, if I want to explain, say, thermal properties, okay, say thermal properties, okay, thermal properties means what? Specific heat, okay, then thermal conductivity, so these are temperature dependent properties. So if I want to explain these properties, I need the concept of lattice vibration, okay. Similarly, not only thermal properties, we want to explain electronic properties or electrical properties, okay, like resistivity, okay, this is specific heat, this is your thermal conductivity K, resistivity, okay, resistivity is your rho. Resistivity is also depend on temperature, okay. When you increase the temperature, the amplitude of this atomic vibration, lattice vibration increases, and it increases your lattice scattering, the scattering of the electrons, okay, and that will change your resistivity, okay. So resistivity also depends on your function of temperature, okay. Similarly, if you want to discuss elastic properties, which is mechanical properties, elastic properties, these properties are also function of temperature, that is vibration. You heat a sample, elastic properties will decrease. So similarly, if you want to explain optical properties, okay, optical properties means when you're shining light, okay, how it's interacting with your lattice vibration, okay, and the quanta of lattice vibration is called phonon. So how light is interactive with phonon, okay. When you're shining light, your sample will get polarized, okay, and this ionic, because light is electric field, and this ionic polarizability also depends on the motion of the particles, okay. So like you are scattering x-rays inelastically with sample, then also this lattice vibration is important to explain, okay. Similarly, for if you want to explain Raman scattering, there also you need this lattice vibrations. So this is a very key concept, okay. In summary, it's a very key concept, especially to explain the temperature dependent properties of solid, okay. Now, in order to understand this, what is lattice vibration, I will start first with the monoatomic one dimensional lattice, okay. So let me start with a monoatomic lattice.
Sir, please wait.
Okay, 1D lattice. 1D lattice. Okay, 1D lattice means I'm considering monoatomic lattice. Okay. Now I have a chain of atom. Okay. I have one dimensional atom chain. Okay, now this atom chain is vibrating. I'm supplying energy. This chain is vibrating. Now I want to know what are the dispersion relation for this chain, because your solid is not continuous. Okay, you have atoms, you have gaps. So atoms are discrete. Okay, so if I consider a linear chain, that will be discrete. So when a discrete chain of atom when vibrate, okay, what are the possible modes? उसके कितने मोड हो सकते हैं, कितनी फ्रीक्वेंसीज हो सकती है, whether there is the limit there's a maximum limit of frequency or not. Okay, so all or whether these vibrations your modes, okay, they are continuous or they are discrete. So to know all these answers, okay, I'm taking the example of first 1D lattice. Okay, so I hope the introduction is clear to you. So I'm erasing now. Okay, can I erase now? So let me erase this one. Is these things now?
Yes, sir.
Okay. Okay. So now I am drawing a one-dimensional atomic chain. Okay. So I have this one-dimensional atomic chain. Okay. So say these are my atoms. Okay. And these atoms are connected with springs. Okay, so say these are springs. Okay, say these are springs. These are springs. And these are spring constant, say beta. Okay, and the distance between say two atom is, or lattice constant is A. Okay, so lattice constant is A. Lattice constant is A. Okay, so I'm taking a chain of atom. Okay, this is, so these are my chain of atoms. Okay, so say this atom is UN. Okay, and this is my nth atom. Okay, I'm moving in x direction since the one-dimensional chain. So say this is it is kept in the x direction. Okay, and say this is my nth atom. Okay, this is my n+1 atom. This is my n+2 atom. This is my n-1 atom, n-2 atom, n-3 atom, so on. Okay, you can keep on adding the atoms. Okay, you can add one more atom here. This n plus, so this is the one-dimensional chain of atom. Okay, now I want to study is dispersion relation. Okay, so I am going to calculate dispersion relation for this monoatomic one-dimensional chain.
Sir,
Huh.
please explain about this chain. You were not audible, my side, please.
So I'm explaining we have a one-dimensional atomic chain of atom. Okay, all these atoms can be assumed to connected with the springs. The lattice constant is between the two atoms A, and the spring constant, okay, is beta is given. Okay, now I want to calculate what are the dispersion relation for this chain. Okay, if this chain is discrete, if I take a continuous string and I calculate dispersion relations, okay, omega dispersion relation means what? Dispersion relation means omega versus k relation. So dispersion relation means what? Dispersion relation is omega versus what is the how omega is a function of k. Okay, dispersion means omega is a function of k. So if I take a continuous string, okay, your omega versus k relation will be linear. If I take a continuous, say a steel rod or a rope, continuous, if I assume nothing is continuous actually. Okay, that all depends on wavelength, which some if you have a higher wavelength, everything behave like continuous. If you have high frequency or lower wavelength, then depends. Okay, so nothing is string, but if you can consider a steel rod or a rope as a continuous. So if I write the dispersion relation for a continuous string, they are always parallel. Okay, you increase the k value, your frequency will increase. K is again related with your lambda. Okay, so you reduce the lambda, your frequency, you increase the k or reduce the lambda. Okay, your omega frequency increases. This is for your continuous string. Now a same relation I want to calculate for this 1D monoatomic lattice. Okay, so let me calculate now. So say these are my atoms. Okay, now I'm giving some displacement to these atoms. Okay, say this is my nth atom. I'm giving a displacement un. Okay, so when I'm giving displacement to this atom, okay, other atoms will also be displaced. Okay, because they are connected by springs. Okay, so say the displacement of n plus atom is un plus 1. Okay, similarly the displacement, okay, after displacement atom will be come here. Okay, similarly the displacement of n plus 2 atom is un plus 2. Okay, similarly the displacement of un minus 1. Okay, displacement for n minus 2 atom is un minus 2. Okay, so on you can keep on going. Okay, so when I'm giving this amplitude or displacement, nearby atom also get displaced. Okay, now I want to calculate how much force is acting on this nth atom. Okay, so if I want to calculate the force on this nth atom, I need the potential energy of this system. Okay, so I'm assuming only nearest interaction is possible. Okay, that means if I take the atom n, so only these atoms are applying force on this atom. Okay, I'm only considering nearest neighbors interaction. Okay, so I'm considering nearest neighbor interaction. Okay, for simplification, that means only these on an atom, only these nearby, which is directly nearest neighbor atom, which is directly connected to this one, they only affect the motion of this particle. Okay, now I want to calculate the force. What is the force on this nth atom? Okay, I need the potential energy of the system. Okay, so let me know what is the potential energy of the system. So when I am giving a stretch by un, okay, this is this spring. So what is the total stretch in the spring? What is the stretch in this spring? You know, potential energy is half kx square. So how much is delta x here? Anyone? Did
un plus 1 minus un.
okay, so I'm giving stretch this one. Okay, so and this particle also moving, this particle moving un plus 1 distance. Okay, this particle is moving un plus 1 distance, and here I'm pushing un distance. Okay, so the stretch will be what? Stretch will be your un plus 1. So if I want to write the this potential energy of this spring, that will be equal half beta, okay, half kx square. That means un plus 1 minus un square. Okay, similarly if I want to write how much force this particle is applying on n, okay, I need the potential energy of this spring. Okay, and the potential energy of this spring will be what should I write? Potential energy of spring will be half beta un minus 1 ka square. I hope this expression is clear. This is the potential energy of this system. Okay, this spring plus this spring. Potential energy of spring this, and spring say spring 1, spring 2. Okay, now my aim is to calculate the force on nth atom. Okay, so once you know the potential energy, you can easily calculate the force. The force of nth atom will be simply
Sir.
del u upon del un. Here displacement is un. Yes, हाँ बोलिए.
सर un यहाँ पोजीशन दिखाने का काम कर रहा है या
हाँ,
फिर
un डिस्प्लेसमेंट है, डिस्प्लेसमेंट मेन पोजीशन से डिस्प्लेसमेंट है. Okay, so and this is the equilibrium position. Now you are giving some displacement to atom from your equilibrium positions. So these are the displacement values. Okay, so when you are giving delta un is displacement, that change in potential energy del u, so the force on nth atom can be given by minus del u upon del un. Okay, please calculate कितना force आएगा अभी. So if I want to calculate
Sir.
the force, हाँ बोलो.
Sir,
हाँ,
here you have taken two atoms.
nearby atoms only.
Okay, means un plus 1 and un.
Yes. Okay, so now differentiate this equation with respect to un. Okay, this will give you 2 cancel हो जाएगा beta beta, okay, un plus 1 minus un, and if you do this will become minus, okay, this minus. Similarly, if you differentiate this expression, this will give you what? Beta, okay, un minus un minus 1, okay. So this is basically what? This is the force on another atom due to n plus 1 atom, okay. Similarly, what is this? This is the force, okay. Okay, force force is spring constant, no? Harmonic oscillator force is what? Kx. So similarly, force on n due to n minus 1 atom is Fn n minus 1, okay. So this is a total force Fn plus Fn n plus 1, and the force on n due to n minus 1, okay. So now I have the force equation, okay. So let me simplify. Once you know the force equation, you can calculate what is the frequency, okay. So by applying Newton's law, so let me solve now for dispersion relation, okay. So I have this Fn, okay. So F I can write m d2 un upon dt square by Newton's law, okay. And if you solve this one, this will give you minus beta, okay, un plus 1, okay, un plus 1 plus un minus 1 minus 2un, okay. So this is your say equation number A. Now I need to solve this equation. So these are my periodic lattice, okay, and I'm assuming the solution of this will be like a traveling wave, okay. So I am giving solution, say un. So un is a exponentially iota k kx minus omega t, okay. So what is this iota kx, na? Kx minus omega t. So iota kx minus omega t type of solutions, okay. So the solution of this waves are, okay, this type. Now just give me 1 minute. Now I just want to solve for, put the values here. I need un minus 1, un plus 1, okay. And you know the position of atoms, okay. Position of atom I can be given as a, if I want to write un, so un will be a e power iota k x. X is for another atom, x is na, okay. So because I have a chain of atom, okay. So suppose this is my zero atom, okay. N equal to 0 atoms, okay. This is n equal to 1 atom, and equal to 2 atom, and equal to 3 atoms. So this will be a, okay. So if I want to reach here x, so another atom x will be my simply na. Similarly for x, for n plus 1 atom will be n plus 1 a. So here I want to write un, the position of x, position of another atom. So the position of another atom will be x equal to na minus omega t. Similarly, if I want to write un minus 1, okay. So un minus 1, this will be simply a iota k n minus 1 a minus omega t, okay. And simply I want to write un plus 1, that will be a k n plus 1 a minus omega t, okay. These are traveling wave solutions. These are traveling wave solutions, okay. Now it's very simple, just put these values in this equation and solve it. We'll get the dispersion relation, okay. Put these values and solve.
Sir, all 4 equations are called traveling wave equations, no?
Yeah,
Or
yeah.
you have mentioned the standard one?
These are all our traveling wave solutions, okay.
Okay.
These are traveling wave solutions, okay. So this is the standard one, okay. So I'm writing because here x is not x is position at atoms, right? So nth atom and n+1 atom, okay. Now just put these values in this equation, okay, and give me the solution. So if I solve this one, okay, so it's very simple. You just need to differentiate un 2 times. So exponential तो 2 बार difference को same ही आएगा. Only you'll get iota. Okay. So what you can write now? Tell me what is solution. So if you do it here, m, okay, you differentiate 2 times this one, you will get again iota kx minus omega t. Okay, so you get iota omega got 2 times. Okay, so you'll get minus omega square. If you put here, similarly minus beta un plus 1 here, you get what?
सर e to the power I k un.
हाँ, तो यहाँ पे क्या आएगा? आयटा na ना, na, got this un. Okay, so similarly if you take here, you get iota power k. Okay, it should come, you should put, you'll get same thing, I think. Okay, e power minus iota k. Okay, and minus 2 exponential iota k na minus omega t. You should get this one, I think. Okay, so
So by putting these 4 equations in
three
equation
equations.
number A,
3 equations. But put the values here. Un plus 1 की value, un minus की value put here, u की value here, and so this factor will be cancelled out. Okay. So if you solve this one, आप लोग का भी ये आ रहा है कि नहीं आ रहा है? Okay. So if I solve this equation, okay, I will get omega square or omega square. हाँ बोलिए.
आ रहा है सर.
आ रहा है ना?
पूरा सॉल्व करके बता दीजिए प्लीज.
भी जैसे ये वाला एक्सप्रेशन है ना, ठीक है, तो इस वाला एक्सप्रेशन पे आप un को 2 बार डिफरेंशिएट करो. 2 बार डिफरेंशिएट करोगे तो क्या आएगा? ये m तो ये आपका जो ऊपर है m तो एज इट इज आएगा. इसको 2 बार डिफरेंशिएट करोगे तो क्या आएगा? a एक्सपोनेंशियल आयोटा kna माइनस ओमेगा t, और क्योंकि t विद रिस्पेक्ट t कर रहे हो तो आयोटा ओमेगा भी आएगा. ओके, माइनस आयोटा ओमेगा भी आएगा. सो माइनस आयोटा ओमेगा एक बार करोगे तो माइनस आयोटा
टाइम्स आएगा तो माइनस ओमेगा स्क्वायर.
हाँ, माइनस ओमेगा स्क्वायर आ जाएगा. ठीक है, तो ये तो आ गया, ये वाला तो आ गया. अब ऐसे ही आपको क्या करना है? बाकी को पुट करना है. बाकी में तो डिफरेंशिएट करना ही नहीं, एज इट इज पुट करना है. ओके, सो जो n प्लस 1 है उसको na प्लस आयोटा k मैंने अंदर रख दिया. ये कॉमन निकाल लिया मैंने, ये वाला फैक्टर जो था उनका कॉमन निकाल लिया. यहाँ पे जो एक n प्लस 1 है तो k रह गया, या माइनस है तो माइनस रह गया, और यहाँ un तो un ही है, माइनस 2 रह गया. इज क्लियर?
So final equation क्या आ रहा है?
So now let us solve the final equation. Okay, so if you solve this one, this will give you m omega square. Okay, beta. Okay, this I can write as a 2 cos k minus 2. Okay, and this give me omega square beta 2 beta upon m, 2 beta upon m, and this will be cos k minus 1, and your omega square will be 2 beta m. Okay, m is the mass of the atom. Okay, and if you solve this one, this will give you 2 sin square k by 2. So if you solve further, okay, this will give you omega equals to under root 4 beta m sin k a by 2. Okay, I am taking only positive value because I need frequency cannot be negative. So I am taking, so this is my dispersion relation. Okay, and if I write this as a omega m sin k a by 2. Okay, so this is the dispersion relation for what? For 1D atomic chain. Okay,
सर
हाँ,
सर इसमें एक माइनस का एक आई थिंक मिसिंग है.
कहाँ पे माइनस मिसिंग?
ओ जो cos k minus 1 तो सर
हाँ,
माइनस 2 sin square k.
अच्छा, माइनस आना चाहिए था ना यहाँ पे. तो
हाँ सर, पहले एक
ये माइनस में इधर भेजा था ना. ये माइनस कैंसिल नहीं हुआ था एक्चुअली, इधर भेजा होगा मैंने माइनस.
हाँ सर.
ठीक है,
कौन सा माइनस बोल रहे हैं आप?
जो ऊपर आया था ना, ऊपर जो माइनस
माइन
ये वाला माइनस आया था ना, वो इसको इधर भेजने पर ही ये उल्टा उल्टा हुआ ना। वरना तो ये ना कुछ कुछ चेंज आ रहा था। या हमको ये चाहिए, हमको टू कॉस के माइनस, सॉरी 1 - 2 कॉस के चाहिए ना यहाँ पे। वी नीड हियर माइनस, सो दिस विल बी एक्चुअली 1 - cos के। ओके, सो 1 - cos के करो तो ये आएगा।
सर, लेकिन वो माइनस हमारा इस माइनस से कैंसिल हो रहा था ना, ओमेगा स्क्वायर का
इधर
माइनस।
इधर माइनस था ही कहाँ? इधर
नहीं
तो
सर, एक्चुअली माइनस माइनस वो एफ
हाँ
इक्वल टू
था वो।
माइनस डी यू डी एक्स, वह एक माइनस सर मिसिंग हुआ था।
अच्छा अच्छा अच्छा,
तो दो
एफ
तरफ
इक्वल
था
टू
सर।
माइनस
सर,
डेल यू डेल एक्स होता है।
अच्छा, देख लेना तुम लोग माइनस का चक्कर क्या है। ओके, लेट मी चेक, मुझे भी चेक करना, तो मैंने कैसे कर दिया। ठीक है,
सर माइनस क्या वही सर,
हाँ माइनस
माइनस कैंसिल हो
माइनस
रहा है ओमेगा।
माइनस तो था ही यहाँ पे। ओके, एंड देन यू हैव कैन -2। ओके, तो कहाँ गड़बड़ हुई माइनस की?
हाँ सर, जो फर्स्ट है ना लेफ्ट हैंड साइड, मेरा उसका ओमेगा का जब सेकंड डेरिवेटिव
अच्छा,
माइनस हो
हमने
रहा
जब
था।
हमने फोर्स लिखा था वो माइनस डेल्यू ओपन करना था हमको।
माइनस डेल यू डेल एक्स
हाँ हाँ
होता है।
हाँ हाँ हाँ,
हम
ठीक
लोग
ठीक,
क्लास
हाँ
में
हाँ, ओके करेक्ट, अब ठीक है। जो फोर्स है फोर्स माइनस डेल्यू ओपन, तो एक माइनस और आएगा एक्स्ट्रा, वो माइनस तो एक माइनस पर आएगा। ठीक है, अब ठीक है। So this is your dispersion relation. Okay, very good. Now we have to analyze this dispersion relation. Okay, or let me plot this dispersion relation. Okay, so if I plot this curve, okay, omega versus k curve. Okay, so this omega will be what? This omega. Okay, so this is the mod of sin k. That means sin k graph तो क्या आएगा? Sine wave आएगा, sine wave. But it's a mod, so I will take only positive values. So this is my graph. Okay, so both sides if you plot, okay, so this is my omega versus k relation, and this frequency, okay, this frequency is maximum frequency omega m. Okay, this is the maximum frequency omega m. Okay, and this value will come what? This k by 2. So this will come out what? Pi by what should maximum will come when this is pi by a, when k is equal to pi by a. Okay, so k by 2, a cancel pi by 2, so this will come on pi by a. So this value is pi by a, this value is 2 pi by a, this value is 3 by 2. what यहाँ पे क्या आएगा? 3 pi by a, 3 pi by a, this is 4 pi by a. Okay, similarly here this is pi by a, 2 pi by a. Okay, and so on. Now we have to see here, because these are traveling waves. Okay, now if I put any k dash which is equal to k plus 2 pi by a. Okay, so you can see here,
Sir,
the frequency has a maximum limit. Yes, बोलिए.
this omega m is maximum frequency ना?
Omega m is maximum frequency. Okay, so omega m is your maximum frequency. Now just give a focus for a few minutes. Okay, what I'm going to tell. Yes, yes.
Omega equal to omega m sine ka.
Omega omega equal to omega m sine k by 2. This omega m is max. Okay.
सर,
हाँ,
आपने प्लॉट करते टाइम कुछ तो बोला कि वैल्यू पाई बाय ऐसे ही लेनी चाहिए सर, मतलब क्यों है, मतलब
बी
वहाँ
यहाँ
पाई
पर
बाय 2 आता है,
बी साइन मैक्सिमम कब होगा? जब ये
साइन पाई बाय 2 को।
जब k by 2 is pi by 2,
ओके सर,
तो k क्या आ जाएगा?
पाई बाय
pi by a, pi by a. Okay, now this, if you in this relation, this is my omega versus k relation. Okay, इसको ढंग से देखो, कोई important point है. Sin k a by 2, अगर मैं यहाँ पे k की जगह k डैश रख दूं, k डैश इक्वल टू k प्लस 2 pi by a, तो मेरा ओमेगा क्या आएगा? सेम आएगा कि क्या अलग आएगा? अगर मैं यहाँ पे k डैश इक्वल टू k प्लस 2π/a रख दूं इस इक्वेशन
सेम
में,
है।
तो ओमेगा सेम आएगा। तो देखो यहाँ पर सपोज मैं यहाँ पर कोई वैल्यू ले रहा हूँ 0, तो 2π/a to 0 plus 2π/a भी सेम वैल्यू आ रही है। If I take some value here k, okay, say this is k1 and this value here, this is k1 plus 2π/a, this value is k1 plus 2π/a. At both the k values you are getting same frequency, isn't it? Are you getting my point? Whether you take this point, same frequency. You take this point, this k value, okay, and this k value is what? This k value is k1 plus 2π/a. You take any k value plus 2π/a, you're getting same frequency value. That means these vibrations are not different. Okay, these two k values are giving same vibrations. Okay, similarly if you go in minus, okay, ये positive k value means, because we have assumed the traveling type of solution, positive k value means the wave moving in right hand side. Similarly the k negative means the wave is moving in left side. So now these k values are same. So these are mixed, these are all same vibrations. तो हमको ये इतना ग्राफ प्लॉट की जरूरत नहीं है. We don't require this much k values. Okay, so the range of k values here, भी यहाँ से लेके ये वापस रिपीट हो रहा है, भी ये वैल्यू ये वापस सब रिपीट हो रहा है. So रिपीट हो रहा है. Similarly माइनस में भी आल्सो सब रिपीट हो रही है. So the range of k is only between minus π/a to plus π/a. I hope my point is clear to you. Okay, so I can take any point and k, and if I replace this point by k plus 2π/a, okay, 2π by interval, so nothing will change. The value of frequency will be same. Okay,
That
so
means you want to say it is periodic, right?
yeah, this is periodic. Okay, this function is periodic. Now this function is repeating. Okay, and the interval is in the interval of period is 2π/a. Okay, now since the 2π, so I am taking this period. Okay, this period is a unique period, and I am assuming all other periods are just you're getting repetition of these things. Okay, in fact this and this also same, this and this also same. You're getting what value here, same what you're getting here, but the minus. Okay, the minus means it's showing the wave traveling in the different opposite directions. Okay, so instead of plotting this all k values, not necessary, because only the interval, these are different, these are unique values. Okay, all others are same vibration, same values. You take any k values here, that 2π plus 2π/a, that will give same frequency. So that is a not new frequency, they are not new vibrations. So what I'm trying to say here, instead of plotting this one, I can just plot here this graph, okay, up to plus π/a and minus π/a. Okay, and here it's getting maximum, and here it is maximum, and this range from k range, okay, from minus π/a to plus π/a, this is called your first Brillouin zone. This is called your first Brillouin zone. Okay, so BJ means Brillouin zone. Okay, I hope the point is clear. Okay, so let me erase this one. इसको मिटा दूं मैं? Can I erase this one? Am I audible or not? Okay, so I'm erasing this one. Okay, so now I want to see, this is my dispersion relation. Now just let's compare with your continuous medium. Okay, just now I have drawn you, I have given you the frequency value. Frequency value was what? Omega sine k/2. Okay, and I have plotted this curve. Okay, so this curve gives me like this, π/a minus π/a, and I told you that this is the graph. Okay, now similarly if you plot this graph for continuous string. Okay, this is for lattice, 1D lattice. This is for 1D lattice. Now, if I draw this graph for a continuous string, okay, for continuous string, I am getting a linear curve. Okay, this is for continuous string. So this is the first difference between a vibration. Okay, the dispersion curve, this is the first difference. If you take a continuous string, then you will get linear curve. Yeah, here you're not getting linear curve. Okay, and here you're getting periodic curves. Okay, and here you're getting maximum frequency. Here there is no limit of frequency. In continuous string, theoretically there is no limit of frequency. You can achieve any frequency. You can give any frequency to your string. Okay, it should vibrate theoretically. But here, when your lattice have a maximum frequency. Okay, it can only the atomic vibration cannot vibrate with the maximum frequency. Okay, that is a second difference between a continuous ring and 1D lattice. Okay, let me discuss a few more points now. Now we have this solution.
Sir, continuous string means we are experiencing that there is a string which is totally continuous inside an atoms that we are imagining, or general.
String means स्टील की रॉड ले लो. ओके, और एक रोप ले लो, कोई भी रोप ले लो. ठीक है, तो उसको वाइब्रेट करो. तो उसमें जैसे सॉलिड है, सॉलिड को आपने हीट किया, तो उसमें जो वेव्स प्रोड्यूस हो रही है उसको कंपेयर कर रहे हैं एक कंटिन्यूस चीज से. ओके, हमारा लैटिस तो हमारा क्या है, डिस्क्रीट है ना. So whenever there is a discreteness of and periodicity, okay, you have there's an upper limit of frequency which is not applicable to this continuous string. Okay, and you can see this lower region. Okay, lower regions omega k relations are your proportional. Okay, so now let me discuss these curve in long wavelength region. Okay, so when to take case number 1, when k tends to 0. Okay, k tends to 0 means because k is equal to what, 2 pi by lambda. So k tends to 0 means lambda is increasing. That means it is a long wavelength region. Now I want to solve this dispersion relation in long wavelength region. Okay, so in long wavelength region, what will become when k tends to 0? When k tends to 0, my sin ka by 2 is equal to what? When k tends to 0, sin ka by 2 कितना होगा?
0 by
0.
0.
K by 2.
K by 2 होगा ना?
K by 2.
Okay, k by 2 होगा. So put the values here. So in long wavelength region, you get dispersion relation as omega m. Okay, k a by 2.
सर
and
k tends to 0 हो गया तो सर sin 0 0 होता है ना सर.
अभी तुमको लिमिट भी पता नहीं है. when sin theta is small, sin theta is equal to theta is small, your sin theta is equals to sin theta. लिमिट ये तो पता होगा ना.
यस सर, ये पता है.
यही तो इसमें क्या है, ये k tends to 0 means ये एंगल है, इसका थीटा ही तो है. So I can write this one as a omega m k a by 2. Okay, now if I compare this now you can see here omega is proportional to k, that you are getting same like a continuous string. Okay, and here vma by 2. Okay, vm a by 2 is equal to v naught. Okay, v naught is what? V naught is the sound velocity. The sound velocity. Okay, in medium. So I can write this equation. Okay, what I'm writing here, that equation also can be written as in terms of this one, to 2 v naught upon a sin ka by 2. Okay, this is also one other way of writing your dispersion relation. Okay, Now, once you have the relation in long wavelength region, okay, you can calculate the phase velocity and the group velocity. Okay, so if I calculate,
सर ये वेलोसिटी को साउंड वेलोसिटी क्यों बोलता है सर?
क्योंकि वो सॉलिड में जो वेलोसिटी जो मूव जिस सॉलिड की इसकी रेंज आती है वो वेलोसिटी की रेंज जो साउंड की वेलोसिटी होती है उसी रेंज की होती है, क्योंकि इसीलिए लैटिस वाइब्रेशन को इलास्टिक वाइब्रेशन भी बोलते हैं। ओके, मतलब जो रेंज आती है वो साउंड की वेलोसिटी की रेंज की इक्वली होती है लैटिस में। जो
एक को एमस्ट्रॉन्ग ऑर्डर पुट करके ये हम कैलकुलेट किया,
ये वेलोसिटी कैलकुलेट कर सकते हैं कितना रेंज आएगा वेलोसिटी का।
अच्छा
ओके,
सच में कुछ साउंड भी प्रोड्यूस नहीं होता है, सिर्फ वेलोसिटी सच में कुछ साउंड वगैरह प्रोड्यूस नहीं होता है।
अगर आप किसी सैंपल को हीट करोगे तो वाइब्रेट करेगा, उसको ऊपर से हथौड़ी से मार दो तो साउंड आएगा, वो भी एक तरह का एनर्जी देने का ही तरीका ही है। ओके, तो जो वेवलेंथ जो होती है वो साउंड जो उनकी जो एटॉमिक वाइब्रेशन जिस वेवलेंथ से वो वाइब्रेट करता है वो सब साउंड को क्या बोलते हैं, अकॉस्टिक रेंज में होती है। सारी जितनी फ्रीक्वेंसीज होती हैं वो सारी अकॉस्टिक रेंज में होती हैं, इसलिए उसको साउंड वेव बोल सकते हैं उसको। ठीक है
सर।
हाँ
सर जब k टेंड्स टू 0 हुआ तो ही लॉन्ग वेवलेंथ रीजन क्या आया?
अरे भाई के तो होता है 2 पाई बाय लैम्बडा होता है ना।
यस सर।
तो के छोटा है तो लैम्बडा बड़ा नहीं हुआ।
ओह ओके सर, ओके सर।
ओके, सो नाउ हाँ, और एनी क्वेश्चन अदर?
यस सर, आपने इधर राइट हैंड साइड में v नॉट इक्वल टू ओमेगा एम ए लिखा है ना सर?
हाँ ओमेगा ए, हाँ इसी को मैंने v बोल दिया कि ओमेगा प्रोपोर्शनल टू k। ओके, एंड द रेशियो इज देयर वेलोसिटी। ओके, सो दिस ओमेगा ए बाय 2 को मैंने लिखा है और इसको मैंने चेंज कर दिया। नाउ यू कैन कैलकुलेट द फेज वेलोसिटी। फेज वेलोसिटी क्या होता है? ओमेगा बाय k। ओके, एंड दैट इज इक्वल टू व्हाट? vm a by 2, and that is equal to sound velocity. Similarly, if I calculate the group velocity is d omega by dk. Okay, just differentiate this equation with respect to k. Again, you get same thing. Vm a by 2 equals to v naught. Okay, that means at long wavelength region, and at long wavelength region, both the group velocity and phase velocities are equal, and they are equal to the velocity of sound. Okay, this is the one thing. Okay, now this I have calculated for what? This thing I have calculated for long wavelength region. Okay, now we have to calculate the same thing for short wavelength region. Okay, just give 5-minute break. हाँ बोलिए।
डी ओमेगा बाय डी के उसके लिए वही एक्सप्रेशन यूज किया ना, ओमेगा इज इक्वल टू 2 v नॉट बाय ए साइन।
हाँ ये दोनों सेम ही तो है। हाँ ये बोलिए।
ओके, गॉट इट, थैंक यू सर।
ओके, सो ओमेगा बाय k भी ये आएगा v नॉट v दिस इज द फेज वेलोसिटी, दिस इज द फेज वेलोसिटी। ओके, and this is your group velocity. So group velocity and phase velocity both are coming same for at long wavelength region for 1D lattice. Okay, so just give 5 minutes break. Okay, we'll start again. Huh?
Sir,
हाँ बोलिए।
group velocity is equals to v delta or v naught?
Group velocity is equal to d omega by dk ना?
Oh no sir, v delta.
V delta what?
Omega m by 2 equals to
omega by k is equal to phase velocity, and group velocity is equal to d omega by dk.
Not that one sir.
Which one?
Omega ma by 2 equals to something sir.
This one?
Yeah.
This is wm a by 2. The same thing. I'm just differentiate this equation na.
Is
I'm
equal to something.
The v naught.
Okay.
V naught, the sound velocity. I have written here also that v naught, the sound velocity. Is it clear now?
Sir.
Okay. just go through this one, and we'll start again in a couple of minutes. Now we'll do this for short wavelength region. Okay.